So 4 electron domains will always result in an electron domain geometry which is tetrahedral. But it doesn't always result in a molecular geometry that's tetrahedral because the non-bonding electrons, they contribute to determining where the electrons are in space, but only the atoms to determine what the shape of the molecule is. We should look at other molecules with different numbers of electron domains. An example is ethylene. Ethylene is a molecular precursor to polyethylene, and ethylene has the following molecular formula. It's 2 hydrogens connected to a carbon with a double bond to a carbon and another 2 hydrogens. So if we pick any one of the carbons, for instance this one, we find that this carbon actually has 3 electron domains. There's one in the carbon-hydrogen bond, another in another carbon-hydrogen bond, and there's another electron domain in the carbon-carbon double bond. So that's 1, 2, 3 domains. The double bond consists of a sigma bond and a pi bond, and the electrons in those bonds cannot occupy exactly the same area of space, but for the purposes of VSEPR, the electrons in the double bond are considered to be contained in the same electron domain. So in this case, we have 3 electron domains, and if we have 3 electron domains, VSEPR electron repulsion decides that the geometry around that carbon atom is going to be so-called trigonal planar. So trigonal planar is the electron domain geometry. Trigonal planar means all the electrons are in the same plane and they define a triangle. And we'll look at that in the computer in a little while. So in this case, all 3 electron domains are associated with atoms connected. And so the molecular geometry, around this carbon atom is also trigonal planar, meaning the bonds define the electron domains, they're all on the same plane, and they define a triangle. The bond angles for trigonal planar geometry, we're going to assume they're all very roughly 120 degrees, and that's going to be a pretty good estimate for most cases where we have these 3 electron domains. Let's have a look at trigonal planar on the computer again and make sure we understand exactly what that means. So here's a molecular model of ethylene on the computer. You can see the 2 carbons and the 4 hydrogens, and this is the carbon-carbon double bond right here. And if we turn it around to look at it from the side, then we can clearly see why this is trigonal planar geometry around this carbon atom. All the atoms lie in the same plane, and they clearly define a triangle. And in this case, both of the carbon atoms are 3 electron domains, both combine to 3 bonds. So the geometry around both of these carbon atoms is trigonal planar. The molecule as a whole is planar, but we won't be able to define a shape for a molecule overall pretty soon as molecules get larger and larger. So trigonal planar geometry associated with each one of these carbon atoms in ethylene. As an example of a molecule with 2 domains, acetylene is actually a pretty good example of this. So acetylene consists of a carbon-carbon triple bond, and each carbon is connected to 1 hydrogen. And here we can see that this carbon atom, for instance, is surrounded by 2 electron domains, 1 in the carbon-hydrogen bond, and in this case, 1 in the carbon-carbon triple bond. The carbon-carbon triple bond consists of a sigma bond, a pi bond, and another pi bond, and the electrons in those bonds cannot occupy exactly the same area of space, but for the purposes of VSPR, they're assumed to all occupy the same domain. So around this carbon atom acetylene, we have 2 electron domains. And the best way to get those 2 electron domains as far apart from each other as they can possibly get is to have a linear geometry. So the electron domain geometry is linear. And again, in this case, at each end of those electron domains there's another atom, and it's the position of the atoms that determine the molecular geometry. So the molecular geometry around this carbon atom is also linear. So if it's linear, the bond angle has to be 180 degrees. And any linear geometry will have a bond angle of 180 degrees. So have a quick look at that on the computer just to complete our examination of these at the computer model level. So here is a computer molecular model of acetylene, the two carbon atoms, the two hydrogens, and this is the triple bond, carbon-carbon triple bond in between these, and we decided this should be linear geometry, which means when we move the molecule around, nothing should change, and it doesn't. So this is pretty trivial, obviously. The molecule's just linear, and of course it's linear of both carbon atoms. We can rotate the entire molecule, but in this case, because everything's linear, we can't change the position of any one atom with respect to each other. So this is linear geometry with respect to this carbon atom and this carbon atom. And in this particular case, the entire molecule is linear, although that definitely will not always be true in all molecules which have two electron domains around an atom. So we can take what we just learned and apply that to any arbitrary sized molecule and any atom within that molecule. Let's take acetone as an example. Acetone is a very common industrial solvent, and if we ask ourselves about the central carbon atom in acetone, we can see there are 3 electron domains. One domain is in the double bond. The double bond counts as a single domain. So we have 3 electron domains, which means the electron domain geometry will be trigonal planar. And in this case, because each domain is associated with another atom, and it's the positions of the atoms that determine the geometry of the molecule, in this case the carbon atom within the molecule, in this case the molecular geometry is also trigonal planar. And all the bond angles are going to be roughly 120 degrees. Remember, non-bonding electrons, they help to contribute to the electron domain geometry, but not the entire molecular geometry. So for instance, pyridine, or more specifically the nitrogen atom in pyridine, if we count the number of electron domains, we find there's 3. There's one in this bond, one in this bond, and there's one in this non-bonding pair of electrons. So again, we have 3 electron domains, which means the electron domain geometry again will be trigonal planar. But in this case, only 2 of the electron domains are associated with other atoms in the molecule. And it's the positions of the atoms that determine the molecular geometry. So in this case, the molecular geometry can only be defined as bent. So the electron domain geometry and the molecular geometry are not the same around this nitrogen atom in pyridine. Ethanolamine is used to trap greenhouse gases in sort of modern implementations in modern powerhouses that generate carbon dioxide. The nitrogen has 4 electron domains. Therefore, the electron domain geometry will be tetrahedral. Remember, the non-bonding electrons don't contribute to the molecular geometry, and so the molecular geometry of this carbon atom will be trigonal, so this nitrogen atom, pyramidal. Similarly, the oxygen in ethanolamine also has 4 electron domains, which means the electron domain geometry will also be tetrahedral. However, in this case, the molecular geometry can only be described as bent, because there are only 3 atoms associated with the geometry around the oxygen. And again, the bond angle here will be roughly 109 degrees. This bond angle will also be roughly 109 degrees. So we have a table here of molecule types, the electron domain geometries, the molecular geometries, and the various bond angles. And this is for reference. We don't want you to go memorize this table. We want you to learn these various geometries by working problems in context. But this is useful little reference material in case you forget some number. It's not memorizing numbers is not what we want you to do. We want you to learn these numbers by using them. If you forget them, there's some reference here. So let's just see how we would use this notation in an actual example. So triethanolamine, for the oxygen, for instance, in triethanolamine, according to the notation of the table, the central atom in this case, this would be, X2E2, where A, the central atom, is oxygen. The X in this case is the bond to hydrogen and also the bond to carbon. There's one X and there's the other X. And E means non-bonding electrons, so in this case there are two pairs of non-bonding electrons. So this is an example of AX2E2. AX2E2 is a tetrahedral electron domain geometry and bent molecular geometry. Again, we don't want to go memorizing that. So we have tetrahedral electron domain geometry and bent molecular geometry. And the central nitrogen atom is an example of AX3E, A being the central nitrogen, X being, in this case, a carbon atom and a carbon atom and another carbon atom, these three carbon atoms, and E is one pair of non-bonding electrons, and AX3E, tetrahedral electron domain, trigonal pyramidal. Again, we don't want you to memorize this, we want you to work this out. So the electron domain geometry, in this case, is tetrahedral. Oops. And the molecular geometry around this particular carbon atom is trigonal pyramidal. Again, that's the geometry around the atom. Because of a molecule this size, we can only talk about the geometry around an individual atom. We can't describe the geometry of the entire, or the shape of the entire molecule, because it will actually have various different shapes at any instant in time. And those shapes will be interconverting very rapidly indeed.